All right, very well. Welcome back. Now, so in the last class, we were looking at something very interesting, something that you can relate to now, right? You have been using these computers for a long time, any computing device. You have been programming. I hope you have had some kind of experience programming it, like some working with some programming language, right? And now we are actually getting into the details about how the program, when you write something, when you write a code, when as the computer executes the code one instruction at a time, what is really happening at the hardware level, right? And how is it, how is the computer able to take decisions on behalf of you? Because of course you are the one who's writing the code, you're letting the computer know what should be done, right? So the brain is still you, but how is it happening at the hardware level? And towards that, in the last class, we started out on the discussion of the conditional flags. So we will do that. So this conditional testing, which enables the execution of codes like these code segments like if-else statements, for loops, while loops. These are all enabled through conditional testing, and the computer does it through the usage of these flags. Okay, so that's the idea behind this. And what is a flag? We have defined a flag in the last class. It's basically a 1-bit indicator. It just indicates the result of an operation. That's all it is. Okay. Now, and in the last class we have looked at two flags. Okay, the Z flag, which basically indicates if the result of an operation. When I say an operation, it could be an addition operation or a subtraction operation. So basically, we are still using the component that you already built, right? So basically, you're using the adder or slash subtractor, and you're adding these flags as additional outputs of that system. Okay. So in the last class, we have seen that we have seen how to build a zero flag. The zero flag, or the Z flag, is basically, you know, the way we defined it is it is set. The Z flag is set if the result of an operation is 0, right? That means the sum bits that comes out of the adder, each individual bit has to be a 0 for the Z flag to be set. And one of you suggested that to implement the Z flag, all I have to do is basically send all of those sum outputs through a NOR gate, and that will basically give you the Z flag. Because in NOR gate, the output of a NOR gate is 1 only when all the inputs to the NOR gate is 0, right, are zeros. Only then the output of the NOR gate is 1. So that satisfies the way we define the Z flag. And so that will tell me when I'm trying to compare two numbers, and I can use this instruction called compare A and B, where A and B are, let's say, two variables, numbers assigned to those variables. I can now use the Z flag to see if A and B are the same, right? Because whenever I use this statement, compare A and B in my program, what's happening at the hardware level is that it's basically executing A minus B operation. Okay, so basically it's subtracting B from A, and if I want to see if A is equal to B, then all I have to do is check for the Z flag, right? So if the Z flag is set, that means A is equal to B. Otherwise, it's not equal. Now, for additional conditional testing, now that depends on how you look at those numbers. Again, I would like to reiterate here that for the computer, everything is zeros and ones. Even your program code is basically ultimately, when you write the program, once it's written, once it's stored in the memory, it's all zeros and ones, right? In the program memory, it's all zeros and ones. So for computer, it doesn't really know what it's working with. It's basically a passive instrument, right? So when we work with numbers, data, which means something to us, again, data can come in, you know, signed data and unsigned data. So in the last class, we looked at what kind of flags are essential to do conditional testing between unsigned numbers, right? And we have basically come up with the C flag, right, in the last class, that can enable us to compare between two numbers. So we have done all the comparisons. We have compared all the different cases. We have A larger than B, A larger than or equal to B, A less than B, A less than or equal to B. So we have derived conditions that can enable us to compare between two numbers A and B. two unsigned numbers a and b. Okay. Now let's extend our discussion, and now we'll focus on comparing numbers that are signed, okay, that have a sign associated with it. Okay. All right. So let's start with that. Let's start with the the diagram of your adder/subtraction circuit. Again, just to give you a very brief overview of the architecture, okay, in a very simplest terms, because of course we're going to learn more in depth about the computer architecture in your next class, in your 356 class. But in this class, let's actually look at it at a very intuitive level, so that you understand what's going on inside the hardware. All right. Okay. So let's do that. So what you have is basically, you're working with this central processing unit, CPU. You already you must have heard this word CPU before. The central processing unit, which basically has your arithmetic logic unit, your ALU. Again, it's basically it can perform your arithmetic operations. You know how to build the ALU already. Your adder/subtraction circuit is a big part of your ALU, really, arithmetic logic unit. And of course, you can add additional aspects to that, additional aspects like bitwise logical operations to this module, okay, which is not very difficult. I mean, that's something that can be accomplished easily. So the important part of this is basically the arithmetic operations. This ALU can perform arithmetic operations. Okay, and then you have what is called these temporary memory locations, if you want to talk about them, if you want to call them, are called registers. We're going to talk about this in more detail later on, but these, for now, just think about these as you have few of them, not many, for each CPU, for each central processing unit. Let's say for your toy computer that you're trying to build, let's say you have two registers, A and B. Okay. Now again, what's the purpose of these registers? And of course, you also have what is called the conditional code register. The conditional code register. Wow. Okay. So what is the conditional code register? CCR. Let me call that CCR. Conditional code register. So what does that do? So basically, it stores the flags. So it stores the values of the flags. So far we have done C flag and the Z flag, right? And then we have to work on other flags as well, and that's what we're going to do today. But again, that's a register where each of these location is 1 bit. Again, when I say this is a 4-bit register. That means I can basically store a 4-bit number in these temporary locations. These are temporary memory locations inside the CPU. And then of course you have the external memory, right? You have the external memory, and in the external memory you store both the program code. So you have the program memory where you store the program code. So when you're writing a program, you need to, especially when you're writing your a program in assembly language, like say you're trying to code a microcontroller, okay, then you have to specify where that code is stored in your memory. Okay, so basically every memory location will have a unique address associated with that. So with address, so you can specify that address as the starting of your program code. And then you have again in the memory you can also store data, right? So that's your data memory. Again, each memory location have a unique code. Okay, so as you're processing, as you're running or execute, so you write a code, let's say an assembly language code, you compile it, and then as the computer executes that code, what it's really doing is basically it's going from one memory location to the next and executing the instruction. So your instructions are again in terms of zeros and ones, okay. And if I want to perform some operations with these data values, these data that are stored in my memory, okay, again this data is all zeros and ones, all right. If I want to perform some operation, let's say you have, let's say this is some address A1, again specified as a binary number because everything is binary, right? Data 1, let's say this is data 2, we call this is stored in a memory location A2. Okay, so if I want to process between these values that are stored in a particular memory location, okay, so in my code I would basically copy these values into my temporary memory locations, and then I use my and then operate between them using my ALU, arithmetic logic unit. Okay. And then once I get the data, I would need to once I get the result, I would basically store the result back into my memory location using a code. So that's how it basically works. And again, at a very basic intuitive level, that's how this computer system is organized. All right. Now let's move forward and describe the flags that are necessary to compare between two numbers A and B, okay, wherein my A and B are unsigned numbers. Now let's ask the first question. Do I need any other additional flags? Can I use the C flag to perform comparison between two signed numbers? What do you think? While you're thinking, let me come up with the circuit of your arithmetic logic or arithmetic RS/subtractor circuit. That looks something like this. Again, let's say that this is an 8-bit adder, A 0 to 7, B 0 to 7. That's your XOR. That's your control. Okay, that's your 8-bit adder. All right, that's your C out. Okay, and we have 8 sums coming out: 2, 3, 4, 5, 6, 7, 8, S0 through S7. Okay, and now let's implement the flags. Again, to implement the Z flag, we have used an XOR gate, an 8-input XOR gate to get the Z flag. And as I mentioned before, this Z flag forms one of the bit of the conditional code register within the CPU. Okay. Now, every time I execute an instruction, all of these flags are being affected. Okay. All right. So let's get back to that. So that's your Z flag, and the way we have implemented the C flag was we used an XOR gate. Again, going back to your previous class, another XOR gate, because we wanted to ensure that my C flag is the same as C out when I'm doing the addition operations. My C flag is the inverted version of C out when I'm doing subtraction operations. Right? So basically I use the C flag, and then I use the control input again here to control what I'm getting as an output right here. Okay. So that's my C flag. All right. Now the question is, do I need any additional flags? Can I use the C flag to perform comparison between A and B? In this case, my A and B are being signed. Okay. What do you think? Any thoughts on that? Different flag, right? Because obviously, just take an example. Yeah, if my A is 7, which is 0, 1, 1, 1. B is 9, let's say, which is 1, 0, 0, 1. Now, of course, in this case, yeah, if A is 7, if I'm considering them as unsigned, let me do this. If I'm given two numbers, let me do the other way. If I'm given two numbers, 0, 1, 1, 1, 1, 0, 0, 1, okay. If I consider these numbers as unsigned, then this would correspond to 7, this would correspond to 9. If I consider the same numbers as signed, then this would correspond to 1, still 7, that's a positive number. It's plus 7, let's say. That's a positive number. My most significant bit is a 0. If I consider this number, of course, that's a negative number here, right? And what is this number? That is minus. That turns out to be minus 7, right? How do I know what that number is? You take the negative or the 2's complement of that number, which is basically 0, 1, 1, 1, and place a negative sign, which is basically negative 7. Right? Now, if I consider these as unsigned, obviously, let's say this is A and this is B. Obviously, A is less than B. If I consider these as signed, obviously A is larger than B. Because A is positive, obviously A is larger than B. Now, if I use my Vflag, because everything that I derived in the last class, where I'm trying to compare between two numbers A and B, I assume my A and B to be unsigned. If I use my Vflag, of course, it will give me the correct result for this particular case. Of course, this is not going to be correct. That's going to be completely opposite, right? So I cannot use my Vflag anymore to do the comparisons between two signed numbers. Okay, so with that said, let me ask you, can you come up with an additional flag that I can possibly use, I can possibly define to compare, to enable me to compare between two signed numbers? Any ideas there in the class? Can you think of a flag? Can you think of another indicator that can enable me to compare between two numbers A and B, where my A and B are signed numbers? So when I'm working with my sign, that's perfect. When I'm working with my sign, as the name suggests, sign, right? I'm looking at the sign. My numbers are signed. That means there is a sign, a positive sign or a negative sign associated with that. How do I test for sign? I test for the sign because now when I'm working with signed numbers, my answer can be signed as well. My answer is a signed number as well, right? So how do I know if my answer is positive or negative? By looking at the most significant bit of the answer. Yes, my answer where this corresponds to the answer. Yes, so the most significant bit of my result, my S7 bit, will be my sign bit. Let me call that the Nflag. So the idea is, in this case, if I'm doing A plus A minus B operation, if the answer is larger than 0, okay, when I say larger than 0, that means it has to be a positive answer. Okay? Positive answer as in my Nflag should be 0. That means my Nflag should be 0, implies A is larger than B. Again, simple logic, yeah, very simple logic here. Because my N, the most significant bit, represents the sign of the resulting answer that can tell me the relative magnitude between those two numbers. All right. Likewise, if my answer is less than 0, which is indicated by my N being a 1, implies my A is less than B. So that's so far so good. So far so good. And we can take some examples. Okay. Let's take some examples. Let's say my A is 1, 0, 1, 0, and B is 1, 0, 0, 1. Okay. Now, what is my A? If these are signed numbers, my A would be minus, take the 2's complement of this would be 0, 1, 1, 0, which is minus 6. Here, we have already done that, so that's minus 0, 1, 1, 1, which is minus 7. Obviously, my A is larger than B, right? And you can check again, how does my Nflag gets affected when I do this operation, compare a comma b. When I execute this operation, basically it's doing a minus b operation, right, and checking for the n flag this time. So let's do that. So my a is 1010. Again, by going through the hardware, how the hardware is processing this information, then it is adding to that, because I'm doing a minus b operation. It's adding to a the 2's complement of b, which is 0, 1, 1, 1. The answer is 1. 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. Okay. My n flag, which is basically this particular, that's my n flag. My n flag is 0. So yes, it works. My a is larger than b, right? Very good. Let's take some more examples just to make sure it works all the time. Now let's say my a this time is 1001 -7. Let me take a positive value this time. 0, 1, 1, 1 corresponds to +7. Now b is 1010. Okay. A this time I've taken this as a +7, and b is 1010, which corresponds to this is a negative number, so that's negative 0, 1, 1, 0, -6. Okay, and let me do the operation again. I'm trying to execute this operation. Compare a comma b. That means at the hardware level, at this level, it's doing a minus b operation. So let's do that. So a is +7, which is 0, 1, 1, 1. In this case, obviously, I can see that a is larger than b, so I expect that my n flag should be 1. In this case, a is larger than b, so when I do the a minus b operation, what do I expect for the n flag? A 0, right? A 0. Because I expect a positive answer. When I do the subtraction, I expect a positive answer. So let's see if I get a positive answer. Here I have 1, 0, 1, 0, -6. So I take the 2's complement of that. That will be 0, 1, 1, 0. Okay. And what do we get? So that's 1. 1 plus 1 is 0, 1. 1 plus 1 plus 1 is 1, 1, 1. The output carry is 0, of course. I don't have any output carry. Okay. Now, what is my n flag? In this case, for this particular case, what does my n flag say? My n flag says it's a 1, because again, what is my n flag? My n flag is nothing but the most significant bit. This is the most significant bit. It says 1. What I expected was my n flag to be 0, because obviously a is larger than b. So I expected the n flag to be as 0, but I'm getting an n flag as 1. So what could be happening here? Why am I getting this weird result? Well, no, this is not unsigned numbers. These are signed numbers. I specified a and b to be signed numbers here, right? Again, just by looking at the numbers itself, I cannot say anything about them unless I specify what those numbers are. Okay? Just by looking at them, it's just zeros and ones. In fact, your hardware doesn't know what those numbers are. From the perspective of the hardware, it's basically voltages, zeros and ones. Either you have a high voltage or a low level or a high level. So that doesn't really, it's not intelligent enough to figure out if these are signed or unsigned. Again, remember always, it's the programmer who knows what he's working with. Okay, so there is obviously something is not right here, right? What could be happening there? No, okay. Well, yes, but again, think about it from the hardware perspective. For as uh, as far as the hardware is concerned, that is the answer you get. It doesn't know that if I get this answer, it has to do something else about that. So let me put it this way. Okay, let me put it this way. Going back to the basics, when I'm working with unsigned numbers or when I'm working with signed numbers, all right, when I'm working with 4-bit signed numbers, what is the range of numbers I can represent in 4 bits? Again, you go from 0, 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, right? That's the range of numbers I can represent. And in terms of the values, I know that I can go from -8 on the negative end, that's the least negative number, to 0. And on the positive side, I got the maximum positive number I can get is +7. That's it. So that's the range of numbers I can represent, or range of values I can represent with 4 bits. Signed numbers. Yeah, absolutely right. We are looking at that. You have to remember that. This is a very, again, so any operation, when I'm doing either it's addition or operation or subtraction operation, that results in a number that's falling beyond that range, I cannot represent that number in 4 bits. You have to remember that, right? In this case, what I'm doing is I'm doing +7 minus of -6, which is 7 plus 6, which is 13. It falls beyond this range, beyond the range of my positive values. So I cannot represent that accurately in 4 bits. If I want to represent the result accurately in 4 bits, then I need to have an additional bit. If I had 5 bits, yes, this would have been the right answer. This would have been my most significant bit, and it would have given me the right sign. Okay. So what is happening here is when I'm doing this operation, I'm having an overflow. All right, I'm getting an overflow. So I cannot just rely on the Nflag to make the decision, especially when I'm working with signed numbers. I cannot just rely on the Nflag. That means I have to have another flag that would indicate when an overflow has occurred. So now let's look at how to build the Nflag. The Nflag is already done. So now let's look at how do we obtain what is called the Vflag. So the overflow flag is represented with the letter V. So that's the Vflag. Okay. All right. Are you guys with me until this point? Does that make sense? Okay. Very good. So let's do that. Now let's examine when we have an overflow in the first place. What conditions would result in the overflow? All right. Let's again simplify our discussion to 4 bits for now. 4 bits. When I'm adding a positive number to a negative number, will I ever have an overflow? A positive number to a negative number. Again, the range with 4 bits we saw -8, 0, +7, right? The range of numbers with 4 bits. So you take any number on the positive side, add it to the negative side. Would that result, is there a possibility for the result to fall beyond the range? No, right? You can take any number, add it to the negative number, the result will always be within that range. There is no question about that number falling beyond the range. When I'm adding a positive number and a negative number from the same range of values, I will have a result that will be contained within that range. So yes, when I do that, there is no overflow. I can confidently state that there is no overflow. Okay. Now what about when I'm adding a positive number to a positive number? Can I have an overflow? It's definitely possible. It's not that every time I add a positive number to a positive number, I will always have an overflow, but there are conditions where I may have an overflow. So yes, overflow is possible. Likewise, when I add a negative number to a negative number, same thing, overflow is possible. So let's look at how do we test for the overflow condition. Now, as we have seen in the last example, right, between when I'm trying to subtract 7 and negative 6, right, 7 minus 6, I should be getting a positive answer, but the answer I got was negative, right. My most significant bit should have been a 0 when I'm considering those 4 bits for the 4-bit answer, but it was a 1, right. So we can go by that observation to come up with a scheme to implement our Vflag. So let me put it this way. So let's say you have 2 numbers. Let's say I'm adding 2 positive numbers, right? So positive number, that means my most significant bit is a 0. That's my most significant bit. And of course, I don't care about the rest of these bits. So that's the first number. I'm adding that to the next positive number, the other positive number. Again, I don't care about the rest of these bits. Okay. So that's the most significant bit position of A, and let's say these are A and B numbers, A and B. That's the most significant bit. All right. And now, when I'm adding these 2 numbers, all right, if I want to test if I have an overflow, that means it should give me an answer that is unexpected, right? When I'm adding 2 positive numbers, I should get a positive answer. I should not get a negative answer. All right. Are you with me till this point? When I'm adding 2 positive numbers, the result should be positive, or the most significant bit of the result should be a 0, should not be a 1, should be a 0, right? So under what circumstances would I get a 1 as the answer here? Let's examine that, because if I get a 1 here, when I'm adding 2 positive numbers, something is not right. I'm not able to express the answer within those fixed number of bits. If I had an additional bit, I would have gotten the right answer, right? That's how I will test for the overflow condition. I'm adding 2 positive numbers. I'm trying to examine under what conditions I would get a 1 here, a negative answer, or a seemingly negative answer. What conditions? I will get a 1 here only when my C in to the most significant bit position is a 1, right? Otherwise, 0 plus 0 is 0. The only way I can get a 1 here is if I have a carry out, or let me put it this way. The carry into the most significant bit position, this is the most significant position, be a 1. Of course, the carry out should be a 0 from the most significant bit position. Only under these circumstances, I will get a 1. Does it make sense? So the carry into the most significant bit position should be a 1, which will give me a 1 in the most significant bit position when I'm adding 2 positive numbers together. All right. Now let's look at, so let's hold on to that thought. Now let's look at 2 negative numbers, A and B, being added together. Okay. So in this case, 1 followed by some whatever that numbers are. I'm adding these 2 numbers together. Again, when I'm adding 2 negative numbers, the answer should be negative. Cannot be a positive number, right? Should always be negative. Now, when I have an overflow condition, then the answer would look like a positive answer, but it's actually not positive, because I'm not able to express the answer in the fixed number of bits. Okay, so I'm adding two negative numbers. When do I get a positive answer? I get a positive answer when my most significant bit position, most significant bit is 0, right? When do I get a 0 here? When I'm adding two negative numbers. I get a 0 here only when my Cin to the most significant bit position is a 0, right? If it's a 1, then I get a 1. Only when my Cin to the most significant bit is a 0, and of course when I add these two numbers, 1 plus 1 is 0, 1, so the C out from the most significant bit position is a 1, right? The actual number would have been this. If I had this additional bit, then of course I would have gotten the right answer, but because I don't have the additional bit, this is considered as a C out, not as part of the answer. Are you with me until this point? So these are the two instances when I can get an overflow. All right. So how do I test for this now? Any ideas on how do we test for the overflow condition? Now, okay, so let's see. So this is good. This is for the overflow. This is the cases where I'm adding two positive numbers, two negative numbers, and checking for the overflow. Let's see what happens when I'm adding a positive number to a negative number. Okay, so let's say my A in this case is some positive number followed by some number. B is, let's say, a negative number followed by whatever that is. Okay. Now let's consider the Cin to the most significant bit to be a 1 in this case. Okay. So that will give me a 0 here, and the C out of the most significant bit position is a 1. Right? The Cin to the most significant bit position is a 1. A C out of the most significant bit position is also 1. In one case. Let's say the other case would be, again you have A and B. I'm adding two negative numbers to a positive number to a negative number. That's 0 followed by some numbers, 1 followed by some bits. Let's say in this case I have a 0 as my Cin to the most significant bit position. So what do I get? I have 1 plus 0 is 1, and my C out of the most significant bit position is also 0. I'm trying to give you some hint here how we can come up with a scheme for the Vflag. Alright? Okay, you see the hint. What should I check? What should I check to configure or to implement my Vflag? Yeah, there you go. Check to see if my Cin to the most significant bit position, C out of the most significant bit position are equal or not equal. How do I check that? What logical gate would enable me to check that? If my Cin and C out are equal, or Cin and C out are not equal. Now let me put that in the form of a truth table. That will AND gate. Well, let's see. Not necessarily. Let me put that in the form of a truth table, and that will be more obvious now. Okay. Cin, again, when I say Cin, that's not this Cin. Okay. Cin MSB, let me call it Cin MSB. That means it's the Cin to the most significant bit position, C out of the most significant bit position. That's the C out. Okay. So 0, 0, 0, 1, 1, 0, 1, 0. You've seen that when my C in and C out matched, we had no overflow, right? That's what we determined. When my C in and C out did not match, we had an overflow. Overflow. When they matched, no overflow. So how do I check for this? What does this truth table correspond to? XOR, yeah? That's it. It's an XOR gate. So in other words, my C in and FB, most significant bit, XORed with C out of the most significant bit is a 1. It's a 1 only when for these two conditions, right? So for the XOR gate, the output of the XOR gate is 1 only for these two conditions. If it's a 1, then I have an overflow. If it's a 0, implies an overflow, or my Vflag should be set. V equals 1 implies no overflow. My V should be 0. Does that make sense? All right. I hope that's clear, yeah? So now I should be able to implement my Vflag. Okay, so what I'm going to do is I'm going to obtain my C in MFB, C into the most significant bit position, all right, and create my Vflag. Vflag. Okay. So I have my C out already here. C in. Another XOR gate. That's my Vflag. Okay. All right. Now I would like to point your attention to the posted slide over there. You see that on the posted slide on the last column, NVVC, right? The NVVC are the flags, and those are the flags. Let me see if I can use a pointer here. All right, right here. So those are your flags, and we have this delta sign symbol, right? What that means is that every time I execute those instructions, the compare instructions in the column, all of the values of the flags, every time I execute those instructions, all the values of these flags are being changed, are being affected. Okay. What is the input to the Vflag? Okay, so I have C out and C in to the most significant bit. So two inputs, C out and C in. All right. So as you can see here, every time I send these numbers in to my adder, all of these flags are being affected simultaneously. All of these flags are changing. All right. Now, so this is a very important point. Again, going back to the question that we raised, right? So when I'm working with signed information and unsigned information, well, okay, let me actually cover one more thing and then we'll get back to that question, because we have not really derived all the conditions yet. For A, in this case, A and B are signed numbers. For A to be larger than B, A to be larger than or equal to B, A to be less than B, A to be less than or equal to B. We haven't done that yet. Right, so let's do that. Let's derive the conditions. What operation should I check for to be able to make these conditions? Just like what we have done in the last class for the unsigned number comparison, let's do the same thing for the signed number comparison. Okay. Now let's actually start with Vflag and Nflag to start with, just the two of them. Nflag, Vflag, and the result of the operation, A minus B. All right. Now I do this operation A minus B, and let's look at all the possibilities: 0, 0, 0, 1, 1, 0, 1, 1. So I do A minus B operation. A minus B are A and B are signed numbers here. I do A minus B operation. I get the N flag as 0. That indicates that the result is positive, right? Most significant bit is positive. I have a B flag of 0. That indicates that there is no overflow occurred. All right, that means whatever answer you got is the right answer, is represented as, within those 4 bits. Okay. What can you say about the result of the operation? The relative magnitude between A and B, when I have N flag and V flag to be zeros. It's positive, yeah. A is larger than B. A is larger than B. Only then I will get a positive. What about the second case where I have N flag and N flag is 0? That means the answer that I got is a positive answer. However, my V flag is set. What does that indicate? My N flag is 0, but my V flag is set. That means even though the answer looks like it's a positive answer, it's really a negative answer because I have the overflow. That means I'm not able to fit the answer in those limited number of bits. Make sense? So when my N flag is 0, my V flag is 1. Even though the answer looks positive, it's actually a negative answer. So A minus B operation results in a negative number. That means my A is less than B. Does it make sense? The argument for the second case? All right. Now moving on. This time I have my N flag to be 1, my V flag to be 0. That means my answer is a negative answer because my N flag is 1. That means the answer is negative, right? And I do not have an overflow. That means whatever answer I got with that operation, that is the correct answer. I don't need an additional bit to make it correct. It's actually correct by itself. I have no overflow there. So what can you say about A minus B here? Or the relative magnitude between A and B? A is less than B again, right? My answer is negative. A minus B results in a negative number, no overflow. That indicates that my A is less than B. Finally, my N flag is 1 and my V flag is also 1. That means my N flag is 1. That means the answer that I got appears as a negative answer because my most significant bit is a 1. However, I have my overflow flag set. That means even though the answer looks negative, it's actually a positive answer, right? Because if I had one additional bit, I could have represented the answer correct with both the sign and magnitude. But since I don't have that additional bit, it appears as a negative answer. So the answer is positive because my N flag is 1 and my V flag is set. That means A is larger than B. Is that clear? Make sure that you understand this, because your next homework would be implementing this entire circuit and simulating it in B2Spice or NI any of your choice of your simulation software. If you have any questions, just let me know. The idea is I want you guys to actually work through this simulation plug in different values and see how this hardware works, how the values of these flags change simultaneously, and how the values of the flag indicate uh, the result of an operation. No, okay, so you will be simulating the gates. So you have these gates in the V2 Spice, right? You have the AND gates, OR gates. So what I would like you guys to do is uh, work as modules. Basically, create the modules and gradually build up your adder/subtractor circuit and add these additional flags to that. But more on that, if you have any questions on the homework, we can talk about that later on. You're welcome to email me and talk about that. All right. So, any questions here until this point about the arguments so far? Okay. Now, how do I check for these? Again, go back to this truth table. Yes. When my Nflag and Vflag are different, my A is less than B. When my Nflag and Vflag are the same, that indicates towards A larger than B. So going back to the same operation, the logical operation between Nflag and Vflag would be Nflag exclusive OR Vflag. If that is equal to 1, what does that point towards? That is equal to 1, that's 1 for these two conditions. That implies A is less than B, right? Nflag or indicates, I'm not at this time I'm not really considering the equal to condition. Nflag and Vflag equal to 0, that indicates A is larger than B. I'm not considering the equal to clause here. All right. So I hope that makes sense. So I need to look at the exclusive OR between Nflag and Vflag to be able to make a decision between the relative magnitudes between A and B. A and B are my signed numbers here. All right. So if I want to consider all the possibilities where my A is less than or equal to B, A is strictly less than B, A is less than or equal to B, A larger than B, A is strictly larger than B, A larger than or equal to B. So if I want to do that, then of course I have to, along with the Nflag and Vflag, along with the exclusive OR operation here, I need to also consider my Vflag, just like what we have done in the last class when we were working with the C-flag. So let's do that. Let's put that information down in another truth table. All right, we know this already. Now I'll work with Nflag and exclusive OR V and Vflag, and the result of the operation in. Okay. Again, my possibilities are 0, 1, 1, 0. Okay. All right. If n exclusive OR V is 0, we've already seen that if n that corresponds to A larger than B. Right? Okay. N exclusive OR V equal to 0 implies A larger than B, and exclusive OR V is 1 indicates A is less than B. Okay. So that indicates A is larger than B, and V flag is 0. That means those two numbers are not the same. That means my A is equal to B. Only then I will get the answer. I'm sorry, not equal. The V flag is not set. This should be A larger than B, strictly larger than B. When my N exclusive OR V flag is 0, that means A is larger than B, or could be larger than B, but my V flag is 1. If V flag is 1, that indicates my V flag is set. That means whatever operation I've done, A minus B operation, resulted in all zeros here. That indicates A is equal to B. N exclusive OR V is 1. That indicates A is less than B. My V flag is 0, so that's definitely A strictly less than B. And again, just like what we've seen last class, you'll see that this particular condition is not never satisfied. So I'll just that. Now, for this particular condition, now let's derive the individual conditions now. For A to be strictly larger than B, for A to be strictly larger than B, my N exclusive or V should be 0, and my V flag should also be 0. That means I need to constrain my V flag to be 0. So I can basically come up with this expression, N exclusive or V plus V flag. So if you notice this expression, that is equal to 0, that indicates my A is strictly larger than B. So I'm placing my V flag here because by doing this and equating to 0, this all terms to be 0, I'm constraining my, so both of these have to be 0 for this to be satisfied. So I'm constraining my V flag to be 0. So that checks for the A strictly larger than the condition. Alright, what about A larger than or equal to B? In this case, I don't care about the V flag. V flag could be a 1. So I only check for N exclusive or B. As long as this is 0, then this condition is satisfied, because this 0 does not preclude the V flag to be a 1. Right? So that can be A greater than or equal to B. That's just for the A greater than or equal to B condition. Alright, so now going for A less than B. A less than B or condition. In this case, my N exclusive or V, that should be a 1, because my when my N exclusive or V is 1, then the V flag cannot be a 1. You already seen that. So that's for strictly less than B condition checking. And for N A less than or equal to B, here I can basically check for N exclusive or V. Either this can be a 1, in which case A is less than B, or V flag can be a 1, in which case A is equal to B. So this condition is satisfied, and if condition is satisfied if either of those are a 1, then A is less than or equal to B. Okay. All right. Let me pause here so that you're able to take in the information and observe that, and let me know if you have any questions on that. Does that make sense? Of course, when you actually implement this circuit, implement these operations, and when you test out with actual numbers, okay, then you will actually see and appreciate how these actually these flags work in principle. Okay, now let's get back to the question that we initially asked. The question is, again, from the perspective of the hardware, it's only dealing with zeros and ones. It does not understand what is signed information, what is unsigned information. Okay? So, then how can we distinguish them? How does the hardware distinguish? Again, it goes back to the programmer. Right? It is the programmer who's giving or who's enabling that hardware to take the decisions. All right. For A larger than or equal to A less than or equal to B, why does that have the same value as A? This. Here can be. Oh, I'm sorry. That should have been a 1. Thank you for pointing that out. That should be a 1. Okay. So either this or this is a 1. This condition is satisfied, and A is less than or equal. Thank you. All right. So it is the programmer that gives value to the numbers. How does he give the value? Okay. So let me let me actually show that. Let me actually show that. Move on to the next slide. Here, going back to the going back to the going back to your instructions, right? When you program it, that's when you specify what numbers you're working with. Now, if you notice here, you have different codes, right? You have the mnemonic, as you can see here. Let me show this. You have the various kind of, these are the branch instructions. Branch. Again, just to recall, just to give a quick recall of what, so I hope you have gotten that down, written that down. The way we work with programs, especially when you're working with assembly language codes, okay, that are much more intuitive, that are much more that requires a much more intimate knowledge of hardware, how the hardware is configured and everything. Okay. If you recall, what we've done, the way with the program works is, you write your code, right, in the program memory. You're executing the instructions one memory location at a time. So you're going one memory location at a time with each clock, with each pulse. Yeah. Okay. Now, so here is some code. Again, all zeros and ones. All right. And let's say you're doing some conditional testing here. At this particular instance, you're using compare statement here. Compare A and B. Let's say. Now, at this stage, A and B are still simply zeros and ones. The hardware doesn't know what it's working with. However, the next statement where you use the branch instruction. This is where you specify what numbers you are working with, A and B. What are these A and B? Are they signed or unsigned? How do you say that? Again, I did that by the branch statement. And again, you can, as you can see here, you have different branch statements. Right? You have different branch statements depending on what numbers you're working with. For example, here, I do the compare A and B operation instruction, and let's not worry about that. Okay. So as you can see here, if I'm using this expression, this instruction BLT, for example, BLT, which basically indicates branch if less than. What do I mean by branch statement? Again, when I say a branch, as the name suggests, my program is not going to be running in the same sequence anymore. It's going to branch to a different location that is specified here in the code, different memory location that is specified in the code. So my branch can happen from here to another memory location and then start executing a different code. Just like your if-else statement. The branch is very similar to your if-else statement in the higher level language. So I have different branch statements here. So if I'm working with A and B to be signed numbers, then I would, in my code, I would specify that to be, let's say BLT, any of these codes, any of these shaded in blue. So BLT would be, I'm testing for A to be strictly less than B, in which case my hardware looks for this particular condition. If this condition is satisfied, it executes that instruction and branches to a different location. If on the other hand, if my A and B are unsigned, then in that case, as a programmer, I would write a different statement. Branch if VLS, branch if lower or same. Okay? Branch if lower or same. In which case, you're specifying to the hardware that it should test. It should basically look upon A and B as unsigned numbers, and in which case the hardware will be looking at these flags, a different set of flags, the C flag and the Z flag. And then if this condition is satisfied, then it basically branches to a different location and start executing the instruction from that location. So to summarize, right? To summarize, it is the programmer who gives value to those members. How does it do that? Through the instruction codes, right? You have separate set of instructions that will be useful, that are used when testing for signed numbers. So when you use that instruction, you're telling the hardware that it should be looking at these flags, N, Z, and V flag. You have separate set of instructions for unsigned operations, in which case you're telling the hardware to look for C flag and V flag. So the flags are enable you to make those decisions, to enable you for the hardware to make the decisions for you. Okay? So that's how it works. All right. Any questions here? Does that make sense? This is a very important concept, because you need to think, or at least start thinking, from the perspective of the hardware. What's happening at the hardware? As for the hardware, it's all connections, right? It's basically you have these different lines going in. These are all voltages. There is no real intelligence in the hardware. These lines goes in. It basically you have this gate switching off and on, and all of these flags are being updated with every instruction code, and it's happening in a very in a way that is reflective of what you have written in the code. So all the intelligence is still in the code. The hardware is configured to execute the code and give you meaningful results. All right. Does it make sense? Any questions on this? Okay, very good. All right. So this will be a very good assignment. I would strongly urge you to start as soon as possible, because it's different from the previous ones. You are actually required, and this is a required assignment. We are required to simulate these and have fun with numbers, so you have a more clear understanding of the happenings at the hardware level. Okay. How long do we have to do this? What do you mean? I don't understand the question here. So you have, I think you have 1.5 weeks for the assignment. And the other thing, and then so I think we can end the class here. Okay. I just want to make a few more announcements, but otherwise the class itself class content is basically ended.